Water bath control is a good example for embedded computing. It shows us software-based control algorithms. It also illustrates two different types of interface circuits. Here's our water bath. We have a temperature sensor, we have a heater, and we have the control system. Let's look at each of these pieces. The temperature sensor is connected to the Arduino using a pull-up resistor. We can get a range of temperatures from the temperature sensor. The heater is connected to a digital output, and it is not directly connected to the Arduino because of the high power levels it requires. The heater is a resistive element. We use this power supply to power the heating element. We use a relay circuit in order to indirectly allow the Arduino to control this high power system. A control output from the Arduino goes to a control input on this circuit. That decides whether the circuit is completed to allow power to flow from the power supply to the heater. This code reads the current value of the temperature sensor and provides it to the control software. Given that temperature reading, we then compute an error between the desired temperature and the current temperature. The control law maintains the current temperature within a range of the desired temperature. That range is plus or minus epsilon. The control law takes as its input the error signal and determines whether the heater should be on or off. If the temperature is outside of the plus or minus epsilon range, it's a simple decision. On if the water is too cold, off is if the water is too hot. When the temperature is within the plus or minus range, the control law uses the previous value as history to determine which direction the temperature is going. Is it going from a higher temperature to a lower temperature? Or is it going from a low temperature to a higher temperature? The loop function in Arduino performs the control action periodically. We read the temperature value, compute an error, compute the control law output to decide whether the heater should be on or off. We then write that value to the digital output that controls the heater. We also write the value to an LED to indicate whether the heater is on. We then go to sleep until the next sample period. We can watch our setup in action. Right now, the heater is off as indicated by the LED. That's because the water is warm enough. We can speed up natural events using some ice to cool down the water. Now the heater is on. We can see on the power supply we're supplying 12 volts and a considerable current. The heater is busy heating up the water. We can also see on the interface board that the digital input controlling the heater is also on. Once again, we can help things along by taking out the ice and then adding some hot water in order to warm up the water bath more quickly. Now, the heater is off because the water is warm enough. So over the natural course of events, the water will cycle between warmer and cooler within that plus or minus epsilon bound. Even though we use very simple control law and digital control of the heating element, we can control the temperature within pretty tight bounds using this simple setup. So we've seen that the water bath controller is a good example. We saw software that implements bang-bang control. We saw an analog input from the temperature sensor. And we saw how to control high voltages and currents with a digital output and some additional circuitry. Thanks for watching.